Now, microinverters. We've mentioned before several times the issue of microinverters, but this is the time I want to go into that particular subject, that matter. Microinverter is per each PV panel. Each PV panel has its personal microinverter. It is installed locally near the panel. We will see pictures in a minute. The DC cable length is minimum. This microinverter receives DC from the panel, immediately, locally convert it into AC and send it to the line. So the distance, the total distance of the DC cable is really kept to the minimum. Which means the maximum AC cable length. But this is less important because voltage drop is significantly higher in DC than in AC. So what I want to do is really keep the DC cable to the minimum length. If we keep the ratio between DC and AC cable length properly, we will lose less. The voltage drop will be kept to the minimum. Another task of the microinverter is power optimization. We will talk about it in depth in a couple of minutes. And one very, very important feature of microinverter, it is the thing that it has its own matrix ID number. If we have a matrix of panels, an array, let's say 100 arrays, every microinverter is connected to every panel, and the microinverter has an address, an XY address in the code in the matrix. And if something happens to the panel, that microinverter reports back to monitoring and control system that this specific panel in an XY coordinate of the matrix is faulty, and it reports what is the fault. So each microinverter has its own ID number. Makes maintenance life easier. Makes troubleshooting simpler. And the most important thing, because everything is simpler and easier to maintain, the uptime of the entire PV array is kept to the maximum, meaning I will not lose energy. Each microinverter has an MPPT, maximum power point tracker. In other words, to continue calculate the maximum I times V equal power, no matter if the specific panel is shaded or faulty or not, to keep the IV at its maximum. It allows us to perform monitoring on the behavior of the system itself, because it senses the outputs coming from the panel, analyze them, and report. All microinverters are connected to data and power bus. Now, data and power bus uses technology, what it called PLC, power line carrier, meaning the data coming out of the microinverter is being transported on the cables. Data on copper. Each microinverter, as we've seen before, has its own address in the matrix. Like we mentioned before, PV panel failure and performances is personally reported. And each PV panel performs independently of the others. This is a very important issue. If something happens to panel number 1, it does not affect panel number 2 in the matrix. They are all performed independently. Typical installation of microinverters. There are two different types of installations. The one on the right, the microinverter itself is mounted in the back side of the panel. Keeping the cables to the minimum, Since the panel facing the sun, the backside is in the shade, no way that electronic device, microinverter, will get heat. It will get hot because of its natural operation, but will not get hot because of the sun. On the left, we see microinverters placed, each of them under each panel in a series, and there is a bus that connects all of them together. Data and power on one line goes out to the grid. This is a slide to compare a string inverter versus microinverter. Microinverters always assures always stable system. And the reason that they do that is because there is a specific microinverter per panel, as we mentioned. Look at the picture on the left, where we have a string inverter. There's a line, there's a string, an array of PV panels. And they're all connected in series. And if one particular panel is faulty, it brings down the total power output of the string itself, or the array itself, on the left-hand side. Because its natural internal resistance will be so high, it will increase the total resistance of the string itself, bringing down the current, bringing down the output power. Now on the right-hand side, we can see microinverters connected to each panel. A personal inverter, small inverter. So if any panel in the string or in the array goes down, the rest of the panels operating independently will not be affected, keeping the total output power to its maximum, even though a particular panel is faulty. Now, because microinverter using MPPT mechanism, circuitry, it keeps the IV, like we said, at its maximum point. That allows locating and installing panels not only southways, not only to the south when the sun is moving and to have the sunbeams directly hitting the surface. We can mount panels on east-west side. And the reason we can do that is because even in lower energy coming into the panel, when the sun rises and when the sun sets, or any time there is a small angle of radiation, the IV multiplication and optimization done by MPPT circuitry within the microinverter keeps it to the maximum. So even in morning hours and in evening hours, I can still receive large amount of energy. The picture on the left, the graphs on the left, present very interesting behavior of a system that have microinverters. The x-axis is the time of the day. The vertical axis is the output power. The red graph is energy coming from the east side panels. The yellow one are energy generated from the west side panels. The blue one is energy generated by the south panels. So the combined energy is the amber color graph. So we capture sunlight early in the morning, we capture sunlight late afternoon, Obviously, we capture the sunlight during midday. The combination of all these increases the power. So the fact is that microinverter has an MPPT circuitry again and again, assuring the multiplication of I times V to the maximum, being the maximum, allows us to place panels looking to the east and panels looking to the west, still receiving a lot of energy, combining it with panels looking at the south, together to get more power. And let's see how microinverters help us in terms of shading. The picture on the left. If there is a string inverter and there is a shaded area across the array, that basically kills tremendous amount of power from all the panels that are affected by the shade, because they are in series. And if a panel is in a shade, its output power is reduced, its internal resistance goes high, it blocks and limits the current that goes through the panels, so we have about 50% or 48% yield. Same shade, looking to the right now, when we have a different configuration of inversion, using microinversion, because of each panel operating independently, only these panels that are in the shade will be affected. Their output power will be reduced. And they will not be reduced to the minimum because the MPPT circuitry within the microinverter. Still, even a shaded panel in an array will provide the maximum amount of power because the MPPT will make sure that its electronics will take the maximum current and maximum voltage, multiply them together to get the highest level of power. That means in the same shaded area between the left configuration inversion and the right configuration inversion, in a right configuration inversion we get close to 98% yield, only 2% loss of output power if we have micro inverters. The fear of fire. Because microinverter is specifically connected to a single panel, if there's something happened to the panel, the microinverter shuts it off and separate it, isolate it from the entire array. It's not the case in large inverters, string or large inverters. A fire in one particular panel, and this panel being connected in series within the array, will affect the neighboring panels. And the fire, like we see on the right hand side, the fire will go from one panel to another. Microinverters limit the chain reaction fire between one panel and another. Microinverters isolate a panel, because anyway it operates independently than the other panels, but it isolates it. So fire will not go in chain reaction. Again, typical technical specification of a microinverter. We will not go into all these parameters. Again, I would like to point out that the numbers are much smaller here because a panel can be 400 watts, so the microinverter has to be maximum 400 watts. So we are talking about less input voltages and output voltages, less input current and output current, less wake-up level, minimum input level of DC voltage coming out from the array to excite the microinverter. That means longer hours of effective PV system.